Hello?
Noah, hey, what's going on, man? I thought we were recording our show today.
I'm sorry, Pete. I forgot to tell you. I think I have math hostitis.
Math hostitis. Oh my God, I'm so sorry to... Wait a sec. What's math hostitis?
It's this rare condition that only affects 1 in 100 people. Usually math podcast hosts.
Well, you sounded fine yesterday. What makes you think you have it today?
I got tested and it came back positive. The test for math hostitis is 99% accurate. So I almost definitely have it.
You know, I wonder what your actual odds are. Did you say only 1 in 100 people have this condition?
Yeah, but I don't see how that would affect my chances now that I've already gotten my test results.
Well, I have some good news for you, my friend. You're not as likely to have it as you think.
Oh, really? Why not? The test is 99% accurate and it came back positive.
Hey, I hear all of that, but I think you and I should talk a little bit about conditional probability, which just happens to be the topic for the Math Club episode 6, Positive Thinking.
Okay, I will humor you on this one, but just to be clear, the question is, if I test positive for a disease that 1 in 100 people have on a test that is correct 99% of the time, what are the chances I really have that disease?
Well, let me ask you a question.
What do you think the answer is? You ask me that all the time, Pete.
Well, what do you think the answer is?
Well, let's see. If my test came back positive and it is correct 99% of the time, then I think I have a 99% chance that I have math hostitis, right?
So let's go back a step or two. First to the general population. So how many people supposedly have this disease?
Let's say, just for the sake of discussing this math question together, that the sample size is 10,000. There are 10,000 people being tested for math hostitis.
Great, got it. So 1 in 100 has the condition. So that means there are 100 people in this population that have it.
Sure. But I really don't see how that's relevant to the question I'm asking, which is what are my chances of having the disease? Because I've already been tested, I've already gotten a positive result, and I know how accurate the test is. I don't think it matters how many other people are out there getting tested or have the disease. In fact, you know what this reminds me of? As an elementary school teacher, there's something that we work really hard to teach kids when they're trying to solve word problems, and that is determining which information is relevant and which information is erroneous or unnecessary to solve the problem. In fact, we'll give kids word problems and we'll make sure that each one of those problems has an extra bit of information in it that you don't need. For example, something like Daniel was born in 1983. He started school in 1988 and he graduated school in 1999. How old was he when he graduated from school? And we want kids to be able to identify that how old he was when he started school is not relevant information to the problem. And we want them to cross that out because you don't need it. And I'm saying in this case, there's irrelevant information that we don't need. Who cares how many people are out there with the disease?
Well, I see where you're coming from. I think it's good to rule out extra data and information that is meant to distract us. But I'm curious to know why you think it doesn't matter knowing what the rate is in the general population. So let me ask you this question. What do you think it means that the test is 99% accurate?
I think that means that out of every 100 times this test is administered, 99 of those times the test comes back with the correct result. And only 1 time out of 100 does the test make a mistake.
Well, let's suppose that you took a test for a disease that nobody has. It's been eradicated from the planet.
Oh, you mean like cavemanitis?
Like cavemanitis, okay? Although I'm pretty sure I knew some guys in high school that had that.
Those guys all work for Geico now.
All right, there goes a sponsor. So, yeah, let's suppose we've got some condition like cavemanitis, and I'm going to give you the test, and it's 99% accurate. So you come back with a positive test result. What does that mean? Do you almost certainly have cavemanitis?
I see what you're doing here.
So easy, a caveman can do it.
No, you're right. If there's a disease that nobody has, and we know for certain that nobody has it, and I take a test that's 99% accurate and I get a positive result, clearly I'm the 1 in 100 that got the false positive.
Right. And if you think about the number of people who will exhibit a false positive, yes, it's 1 in 100, but if you have a very large population base that you're sampling from, you are going to get many, many people who test falsely positive. Maybe you're one of those people, and maybe you don't have this condition. I think we probably need to dive into the numbers a little bit.
I think you're right, because if 0% of the population had this disease and I got a positive, I would not think I almost definitely had it. And now we're just saying, what if 1 out of 100 people has this disease? That's not going to make my odds suddenly jump all the way up to 99%, is it?
No, it's definitely not.
God, it feels kind of silly now that I just jumped to that conclusion. Now that you've kind of explained it that way, it seems so obvious.
Well, it turns out there is a fairly well-known and well-documented phenomenon called base rate fallacy. The base rate fallacy is people's tendency to ignore or minimize background information in favor of individuating information like a test result. In your case, you're saying, hey, I took this test and it has a 99% accuracy rate. Therefore, I'm almost sure to have this condition. That is actually ignoring the underlying facts about the population. You said only 1 in 100 people have this condition. So that definitely needs to show up somehow in the calculation about what is your real chance of having this condition.
Then how do we do the math to calculate what my actual odds are?
Okay, we have a population, say, of 10,000 people. So this population can be split up into 4 subgroups. For example, one of the subgroups, this will be people who do not have the disease and yet test positive for it when they take the test. So we call that group the group of false positives.
Okay.
There are 3 other groups. Do you want to take a stab at what they might be?
Sure. Well, I guess there's also going to be a group of people that don't have the disease and test negative, which we could call true negatives.
Yep.
And then there's going to be all of the people that actually do have the disease. And I guess they're going to divide into 2 groups also, aren't they? They're going to be the actual positives where the test does what it's supposed to do. And then there's going to be a group of false negatives. There's going to be some people that have the disease that test negative.
That's right. So to determine whether or not you actually are positive, we only need to look at 2 of these groups, namely the true positives and the false positives.
You got to accentuate the positive.
How come only those 2?
Well, you tested positive, right?
Yeah.
So you are in one of these 2 groups. To figure out the odds, you've tested positive. Are you a true positive or are you a false positive? We know you're not a false negative or a true negative because you didn't get a negative test outcome. You got a positive outcome.
Right.
So what we need to do is to compare the relative sizes of the true positive group and the false positive group, because you are in fact a member of one of those 2 groups. And depending.
Okay. Okay.
Yeah.
And then we want to see how much bigger the group I'm in is compared to the other group to figure out the chances that I actually am a true positive.
Right. And as you said at the beginning of the episode, you're 99% sure you have it. Well, let's see if the true positive group is 99 times as big as the false positive group.
All right. So let's figure out how big each of those 2 groups is.
Perfect. That sounds good. So we have 10,000 people in the population, and we are assuming that 1 in 100 has the disease. That means there are 100 people that have it. So what does the accuracy of the test tell us about the results on this subgroup of people?
Well, the test is going to be accurate 99% of the time. So if there are 100 people in the population that actually have the disease, 99 of them are going to get the true positive result that we would expect.
That's right. So the group of true positives consists of 99 people. Out of the full 10,000, 99 of them will get a positive test result, and in fact, they have the underlying condition.
All right, let's put that 99 in a box and save it for later, and let's figure out how big the other group is.
Okay, now we need to figure out how many false positives there are. So what is a false positive?
That's going to be somebody that doesn't have the disease, but as luck would have it, gets a false result anyway, a false positive.
Exactly. So how many people in the population do not have mastocytitis?
There's 10,000 people in the population, and we already said that 100 of those people are sick. So that means the remaining 9,900 people don't have mastocytitis.
Right. And so, again, given the accuracy of the test, how many of those people will falsely test positive for this condition, even though they don't have it?
Well, that's 9,900 people, and 1% of them are going to get a false positive, which, oh my goodness, it's also 99.
Bam! So it's the same size group, right?
So wait a minute. Does that mean out of 10,000 people, you're going to have like 198 positive tests? 99 of those are going to be real positive tests, and 99 of them are going to be false positive tests from people who aren't even really sick?
That is exactly what it means. So
This is starting to sound awfully a lot like we're saying my chances are only 50-50.
that is what we're saying. Your chances are 50-50, not even close to 99.
Oh, I'm floored. Wait, so we're saying, just to be clear, that if 1 in 100 people have this disease and I take a test for it, that's 99% accurate, and my test comes back positive, that only means I have a 50-50 chance of having the disease?
Yeah, I mean, the bad news is that you could have the disease with probability 50%, but you also could not have the disease with that same probability.
Well, that's a lot better than the 99% I was thinking.
Isn't it? It's a lot better. So I think this is a surprising result, and I think it nicely illustrates the base rate fallacy. So here, the background information for this problem is there are 10,000 people and only 100 of them have the condition. But your 99% accurate test result that you got is looming large in your mind. And for that reason, you're likely to go, I probably have this. And that's, I think, why you were feeling really sick when I called.
Right. I think you're right. So earlier when we were starting, I was saying that the size of the population and how many people in the population have the disease is extraneous information. And obviously, that's not all extraneous information. But now I'm wondering, is the size of the population important to figuring out my odds? Or was it just the rate of what percent of people are sick?
Yeah, it's just the infection rate that matters, right? And in this problem, we have an infection rate of 1 in 100, which, you could think of as a probability in and of itself. 1 over 100 is 0.01. Probabilities, of course, are numbers between 0 and 1, including 0 and 1. And so we could reframe this problem in the language of probability. In particular, we could talk about conditional probability, because that is the kind of calculation that we're making here. And there is a very neat way to answer this problem using a theorem called Bayes' theorem. So let me tell you what Bayes' theorem says.
Actually, Pete, usually I'd say go ahead, but I think you're going to be excited about this. For today's episode, I invited a special guest who also knows a lot about math.
A special guest?
Yeah, are you ready? Okay.
Yeah.
Alexa, what is Bayes' theorem?
According to Wikipedia, in probability theory and statistics, Bayes' theorem, named after Thomas Bayes, describes the probability of an event based on prior knowledge of conditions that might be related to the event.
So Alexa has gotten us off to a good start here.
By the way, she is a very cheap guest, too.
She's always waiting around to help out. So what our guest is alluding to here is that you have some information that impacts whether or not you might have this condition, right? You took a test and you have the knowledge that you tested positive. So
Right.
the probability now of whether or not you have the condition is not just like 1 in 100, which is true of the general population. You need to factor into that estimate the fact that you just tested positive. So Bayes' theorem, and more generally, conditional probability, gives us a way to do that.
I see. So then how does conditional probability apply to this problem?
Well, let's illustrate that with an example. So suppose that you have just a regular six-sided die, the kind that you would have in any board game. And let's talk about a couple of different events whose probabilities we want to calculate. So the die has six sides. It's a fair die. It's going to land on any one of those sides with equal probability, right? 1/6 of the time. So we can ask, if you just throw the die out there, what is the probability that you will roll an even number?
Well, that would be 50-50 because there's 3 even numbers and there's 3 odd numbers.
Great. So now let's talk about a second event. What is the probability that you will roll a prime number?
The prime numbers on the die are 2, 3, and 5. So again, 3 out of 6 numbers. So that is 50-50.
Okay. Now let's do an example with a conditional probability. So I want you to tell me, Noah, what is the probability that you will roll something even, given that you have rolled a prime number? So you already know, you take it as given that your roll has produced a prime number. And now I want to know, what is the probability that it is an even number?
My intuition would say that there are 3 prime numbers I could have rolled, which are 2, 3, or 5. And only one of those numbers is even. So I'm going to say 1 out of 3, 1/3.
And you're right. So the probability of rolling an even number, absent any additional information, is 1/2. However, if I give you the additional piece of information that, oh, by the way, you've got a prime outcome, then the probability changes to 1 in 3. So this is an example of conditional probability. You are asking the question, what is the probability of one event occurring given that some other event has happened?
I see. And that other event has a bearing on the total outcome, just like in the main example we're discussing. My positive test isn't the only thing that we have to consider. We also have to consider it's a positive test in an environment in which 1 in 100 people have this disease.
Yeah. And so what we have effectively calculated with the 50-50 calculation that we did earlier is that the probability that you have mastocytitis, given that you have tested positive for it, that probability is 1/2, 0.5. That's definitely different from 0.99, which measures the accuracy of the test. So it's very interesting to see how this conditional information can be brought in, and it really changes the overall calculation of the probability.
I see that. Now, both bits of information went into determining the final odds.
Yeah.
What are the odds if I get a negative test that I actually have the disease? Is that 50-50 also?
No, it would require looking at a different pair of subsets of the population, namely the people who have tested negative.
Even without looking at the actual numbers, I can already tell that the people who don't have the disease far outweigh the people who do. So the true negatives is going to be a huge group, and the false negatives is going to be a really small group.
Right. In fact, I have already computed this quantity. The probability of having the condition, given that you have tested negative for it, is 1 in 9,802. So if you get a negative test, you can be pretty sure that you don't have it.
Right. And that's pretty counterintuitive also, because before this discussion, I would have assumed if I got a negative test and the test was 99% accurate, that would mean I had a 1% chance or 1 in 100 chance of having the disease. But you're saying it's actually 1 in 9,800 something.
Yes. So, I think what's happening with these tests is, even though they are not 100% accurate, they have a kind of amplifying effect. So we know the base rate here for the population is 1 in 100 people have this. If you test positive, that number kind of balloons up to 50-50, to a 50% chance of having it. On the other hand, if you test negative, then the 1 in 100 shrinks down to 1 in 9,802. So the test definitely gives you information, but you cannot be as certain as you think based on the accuracy that's reported for the test.
Something that our listeners might enjoy seeing is a project that I created in Scratch that illustrates what your chances are of actually having the disease with a positive test, depending on the two variables we've been talking about, namely what percentage of the people in the population have the disease and what the accuracy rate of the test itself is. In the Scratch project, I put sliders so that you can easily change both of these numbers to see how it affects your final chances of actually being infected.
You can find that at bit.ly/mathclubpodcast-ep6 for episode 6. And we'll also put a link to that project in the show notes so listeners can take a look and play around with that.
Yeah, that sounds great. The application will give people lots of chances to kind of play around with this and see what surprises them and what doesn't.
And in other news, we're introducing a new recurring segment this week. In this segment, we're going to give you some homework, Math Club.
Homework. Why would we do that to our listeners?
Because we're teachers, obviously.
Fine, but oh, wait. Are you talking about the puzzle? Well, that's actually fun. So here's the deal. We will share a mathematical puzzle and let listeners think about it over the next 2 weeks. So, Math Club, if you think you have an answer to the puzzle, we'll provide a place where you can submit it to us.
Then in our next episode, we'll talk about the correct answer and give a shout out to the first person who submitted it. We don't have a name for this segment yet, but we'd love to hear from you about what you think you'd like us to call it. So if you have an idea, drop us a line at mathclubpodcast@gmail.com. And now, here's our first puzzle.
All right, here goes. An explorer walks 1 mile due south, turns and walks 1 mile due east, and then turns again and walks 1 mile due north. When they're done, they find themselves in the exact spot where they started from. So the question is,
Pete, hang on. I think all of our listeners know this one. Is this the one about what color is the bear?
Well, yes and no. The question I was going to ask is, where did the explorer start from? And you might think there's only one answer here, but actually there's more than one. So my challenge to our listeners is, can you come up with an answer other than the North Pole?
Hoo-boo. Now that's a good one. If you think you have the answer, head on over to bit.ly/mathclubpodcast-puzzle1 to submit it. We'll also put that link in our show notes.
And if you're the first one to get it right, we'll let everyone know in our next episode.
Well, as always, Pete, that was an enlightening and fascinating conversation. And I really feel like I learned something I didn't know before about conditional probability.
I definitely think you learned something that you didn't know before. So, congratulations.
Thanks. And speaking of thanks, we'd like to extend our heartfelt thanks to our special guest this week. Alexa, thank you very much for joining us and for helping us to explain Bayes' theorem.
Oh, it was my pleasure, you guys. The Math Club is my absolute favorite podcast. Thank you very much for inviting me to be a part of this episode.
Pete, would you like to tell listeners how they can reach us if they have comments or questions or would like to suggest future episode topics?
Yes, definitely. So send us an email. Our address is mathclubpodcast@gmail.com or find us on Twitter. Our handle is @mathclubpodcast.
And also, if you're so inclined and you like the show, please don't hesitate to rate and review us on Apple Podcasts. That definitely helps to grow the Math Club membership. And if you know someone who loves math or who you just think might love math, please share the show with them. The more the merrier.
Yes, and if you suspect that you or a loved one has math host-itis, by all means, please reach out to your medical provider.
Right. And if you think you or a loved one has cavemanitis, please check in at your local Museum of Natural History.
Thanks, everybody.
We'll see you next time.